Okay, so just like Dr. Jekyll and Mr. Hyde, or Jake Sully and his avatar in the Navi world, also in mathematics, a structure may happen to have an alter ego which lives in a completely different world. This takes the mathematical form of a categorical duality. Categorical duality, so it's a bridge between two worlds. In this talk, we will see that the bridge connects usually geometry, so objects with a geometrical flavor and objects with an algebraic flavor. And in these two sides, the same information is encoded, but in a very different language. We can think of categorical dualities as an improved version of a representation theorem. Often, a representation theorem is shows how abstract algebraic objects can be concretely represented using some topological or geometric object. And categorical dualities go farther. They make this correspondence between the algebraic objects and the topological objects bijective, and they allow us to use this correspondence with its full power. So, and this allows to translate faithfully problems from one side to the other, problems and solution, so theorems, intuitions, across the two worlds. Here we will do a short journey through three categorical dualities. One is from the 30s, this celebrated stone duality, which connects topology and logic. Here, the algebraic structures are called Boolean algebras. Then we will jump ahead of 5 years, more or less, and we'll see Yosida duality, which connects topology with certain structures, mainly coming from functional analysis. And then in the end, we'll see a recent duality, which brings the two under the same umbrella. Okay, let's start with the stone duality. The history here starts with George Boole in 1847, who formalized the rules of propositional logic. So he introduced what is now called Boolean algebra. Boolean algebra is a set B. Think of the elements as propositions, equipped with certain operations, two binary operations and an OR, and a unary operation negation, and two constants, two elements, 0 and 1, also called false and true. And in order for this structure to be a Boolean algebra, they should satisfy certain laws. Here I've written some. For example, P and not P is false, P or not P is a true, P and Q is a Q and P. But these are familiar not only from logic, but also from what you know from basic set theory about the subsets. So for example, if you take a set X and you consider the power set, so the collection of all subsets, they also form a Boolean algebra. So here you just round a bit the end, and you turn it into an intersection. The OR becomes a union, the negation a complement, 0 is the empty set and 1 is X. And this is a Boolean algebra. It satisfies all these laws. And more in general, if you start from a set X, any family that is closed under intersection, union, complement, and contains empty and X is a Boolean algebra. And Stone's amazing result is that, well, Stone is a functional analyst. He needed certain Boolean algebras associated to certain Banach spaces, and he needed a representation theorem, which he then invented, which is that every Boolean algebra, in fact, is isomorphic to a field of sets, so to a family of subsets of some set X. So every Boolean algebra can be realized concretely as an algebra of subsets with intersection, union, and complement. Okay, so we can reason about these abstract things which are Boolean algebra just by imagining to have some subsets and familiar operations. Okay, now we have a representation theorem but Stone proved much more. So at least if you express it in the language that nowadays we have, he proved a categorical duality. For having a categorical duality, we need two ingredients. Let's see what these are. So first ingredient. So a Stone space might have different representations, but there is a canonical one, the only one which is both separating and compact. Okay. These properties can be, so we're familiar to mathematicians of that time because topology was already in place, and so Stone used the terminology of topology. In fact, he defined Stone space, what are nowadays called Stone spaces, which are compact spaces, such that if you look at the closed open sets, so the closed open sets always form a Boolean algebra because they are closed under finite unions, finite intersection, and the complements. In particular, Stone spaces are those compact spaces where these closed sets separate the elements. So just the easiest example is any finite discrete space. Here is compact, and the clopens are all subsets, so they, in particular, the singletons, and they separate elements. And Stone discovered that there's a bijection, up to isomorphism, between Stone spaces and Boolean algebras. So every Boolean algebra arises from a Stone space by taking the Boolean algebra of clopen subsets. And there's actually a unique Stone space that represents that Boolean algebra. So, for example, an infinite discrete space is mapped to its power set, because all the clopen sets are precisely all subsets. In general, so every finite Boolean algebra is the power set of some finite set. Okay, so we have our first ingredients, our one-to-one correspondence between Stone spaces and the Boolean algebras. Is that also not only Boolean algebras can be represented, but also Boolean homomorphisms can be represented. So if I have two Boolean algebras, A and B, then the interesting functions from A to B are the Boolean homomorphisms, so the functions that preserve the Boolean structure. And any Boolean homomorphism can be represented if you choose the canonical representation of the Boolean algebras. So the Stone space can be represented by continuous functions from the Stone space, but this time not from the Stone space of A to the Stone space of B, but vice versa, from the Stone space of B to that one of A. And as an example, if I have a function between finite discrete spaces, and let's say an embedding, a space Y in a subspace X, this induces a Boolean homomorphism in the other direction, from a power set of Y to the power set of X. You associate to a subset A of Y a certain subset of X, which is the intersection of X. This is a homomorphism. And actually, all surjective Boolean homomorphism arises in this way, by an inclusion of spaces and just this easy to understand function, which intersects with the subspace. In more general, also all Boolean homomorphisms, also if they are not surjective, they arise in a manner which is similar to this. And the ingredient, stated in its full flavor, is that the Boolean homomorphisms from A to B are in bijective correspondence with the continuous functions from B to A. From the Stone space of B to the Stone space of A. Okay, so Stone duality states this, that we have a one-to-one correspondence between Boolean algebras and Stone spaces, and moreover, a one-to-one correspondence between the interesting function. And this can be phrased in the language of category theory that nowadays we have. And here, very roughly speaking, a category consists of a class of structures, in this case, Boolean algebras, and a class of maps between them. For example, Boolean homomorphism. satisfying certain laws. And but we'll not go into the formal definition of a category. But a categorical duality is a bijective correspondence between two categories, but reversing the direction of the map. So stone duality, its full power says that there is a categorical duality between the category of Boolean algebras with Boolean homomorphisms and the category of stone spaces with continuous functions. And so now, once we have the duality, we can translate problems. We can translate problems. Let's see just an example of a problem that can be phrased, for example, in the logic terms. And we'll see how it translates to topology, where the things are easier. So if I have a propositional theory T in a language L, so let's say I'm writing a novel and I write some description of the universe in which the novel is. And let's take another propositional theory T prime in the language L prime. Let's say that someone else writes a novel in a universe, about a universe which is disjoint from mine. Okay. If I take the two theories, if I add to my theory of my description of the universe also his, can I deduce more theorems about my universe if they are completely unrelated? Okay. This is roughly the interpretation. So in algebraic terms, this means is the coproduct map from A to the coproduct of A and B between Boolean algebras injective. So here I'm using a technical term, which is coproduct, but I will not define it. And in Boolean algebras is not that simple to describe. But if we go to the topology side, this means is the projection from a product of two stone spaces xy to x surjective. And here this is easy, it's just the usual Cartesian product. So just think about sets. Is the projection of a product of two sets into the first one surjective? What do you think? Yes, I see some people say yes, some people that say never, some people that say sometimes.
One of them is an empty set.
Right, correct. So always except if y is empty and x is not. Right, so almost always, except if y is empty and x is not, and then we can translate it back to algebra and say, oh, the product is always injective, except if b is trivial and a is not. And then we can translate it back to logic and say, okay, if I add to my theory the theory of someone else that writes about a different universe, by adding the theory, I cannot add any new theorem, any new description of my word, except if his theory was inconsistent and mine was not. If his theory was inconsistent, then he can prove falsum, and by adding it to my theory, falsum is also something in my own language, and so I can prove something that was not provable before. This is just an example of how to translate things. Okay, so just as a recap, stone duality is a bijection between Boolean algebras and stone spaces, which also goes to functions, and this allows us to translate problems and results. Let's go to Yosida duality. So after stone result, many mathematicians discovered that various structures can be represented similarly as algebras of real valued or complex valued functions over some compact Hausdorff space. So we got several representation theorems. Here I've written some of the names and some of the structures. Let's focus on the just for the next slide to the most famous one, which is the Gelfand-Naimark representation theorem, which is a bit more general than this, but in this form it says that each unit-cell commutative C-star algebra, whatever it is, if you don't know, we only mention it in this slide, is the algebra of continuous complex valued functions on a compact Hausdorff space. And in fact, this is a duality between unit-cell commutative C-star algebras and certain natural maps between them, and compact Hausdorff spaces. So also functions can be represented, also morphisms of unit-cell commutative C-star algebras can be represented as continuous functions between compact Hausdorff spaces, and we have a precise correspondence. So we can use intuition from topology. But now, we will not do C-star algebras, we do something a bit more simpler, because instead of taking complex valued functions, we take real valued functions, and this gives us Yosida duality. Okay, let's see. So, remind me, how much time do I have?
Still 40 minutes, or
Let's say 30 minutes.
35.
45. Okay, so for a compact Hausdorff space X, the set of real valued continuous function on X has many natural operations. For example, the pointwise sum, the pointwise maximum and minimum, so the binary suprema and binary infima of two functions, scalar multiplication, and constant function 0 and 1. So these operations are enough to recover the space X from this C of XR equipped with this structure. So let us see, however, what are the axioms, how to axiomatically capture C of XR with this structure. Well, first of all, it's a vector lattice. So it's a vector space, a real vector space, equipped with a lattice structure, a lattice order. So a partial order with binary suprema and infima, which has this compatibility property between the order and the real vector space structure. It is translation invariant, so if x is less than y, then x plus z is less than y plus z, and it's positively homogeneous. So if x is less or equal than y, then lambda x is less or equal than lambda y for every positive scalar of lambda. To get a full description, we need to add a bit more structure. Namely, we need to add a designated element 1 and some more. And a further axiom, which is the following. So let's call metrically complete unital vector lattices the following things. And the idea is that this will axiomatize the things of the form C of XR for XR compact Hausdorff space. So it's a vector lattice with an element 1 such that the following function defined over v squared defines a complete metric. Now I'll read before reading what is the description of this expression, let me just mention that in C of XR, if we take as 1 the constant function 1, this function is a uniform metric. In general, we can define it as the infimum of all lambda, such that v minus w is between minus lambda and lambda. Okay. So this defines the metrically complete unital vector lattice. And Yosida proved that every metrically complete unital vector lattice is isomorphic to C of XR for a unique compact Hausdorff space X. And he proved a little bit more. Let's say in modern language, we would say that the category of metrically complete, of compact Hausdorff spaces is dually equivalent to this category of metrically complete unital vector lattices. And here, for example, if I have an inclusion of spaces from X into Y, I get a function from C of YR to C of XR, so in the different direction, which is just the restriction. And in fact, this preserves all the relevant structures, so it's a morphism of metrically complete unital vector lattices. And in fact, every surjective morphism is of this form, is a restriction. And in general, there's every morphism can be represented similarly via a function between compact Hausdorff spaces. Okay, but this allows to translate faithfully problems from the world of metrically complete unital vector lattices to compact Hausdorff spaces. Okay, and just to conclude, we have a third part, which is a duality, which somehow is an umbrella for both dualities we've seen. So we have seen two dualities. The stone duality between stone spaces and Boolean algebra, and you see the duality between compact Hausdorff spaces and metrically complete unital vector lattices. Now, every stone space X is also in particular a compact Hausdorff space, because if you remember, different points are separated by a clopen, but a clopen is an open which is a closed, so in particular its complement is an open, so they are in particular Hausdorff spaces with a separation action which is actually stronger. So we get two different associations. So stone associates to it the Boolean algebra of clopens of X, and Yosida associates to it these other objects, C of XR, which is much more continuous, while the Boolean algebra is more more discrete. By the way, the clopens can be thought also as the continuous functions from X to 0, 1 with the discrete topology. So there is already some similarity. And now what we do is we recall a class of algebraic structures that somehow can specialize in two directions. To something similar to vector lattices, if on one extreme, and something similar to Boolean algebras on the other. And then we'll see a duality which specializes in two directions, to stone duality on one extreme and to Yosida duality on the other. Okay, now, for this we observe that in Yosida duality, this C of XR has a genuine addition. And in a Boolean algebra, you have X join Y, X or Y, which behaves like an addition, but only when X and Y are disjoint. And in order to see them in the same word, we might do a slight tweak to Boolean algebras and embed Boolean algebras into an algebraic structure where a true addition is defined. So for example, instead of 0, 1, we will look at Z. Okay, and now a common abstraction is the one given by lattice-ordered Abelian groups. These are just like vector lattices, but without the scalar multiplication. So we have an Abelian group, we have a lattice order, which is translation invariant. And if these lattice-ordered Abelian groups are very, very highly divisible, they become something similar to vector lattices. If they are poorly divisible, like that, they look like Boolean algebras. Oh yes, and there are some connections to MV algebras, which are the algebraic semantics of Łukasiewicz many-valued logic, which also was the motivation for which some of my co-authors and I looked at these things. But forget it for this talk. And so here we can define similarly to metrically complete unital vector lattices, metrically complete unital Abelian L groups. Here the only thing that differs is that we cannot use scalars anymore, but to define the distance, but rather we have to use rational numbers, and so and bring the denominator here to this definition to make sense. Okay, just as an example, given a compact Hilbert space X, again, C of X R is a metrically complete unital Abelian group, but also C of X 1 over nz, or just as a special example, C of X z. But we can also mix the values of the function can take at different points, and that's what the key for our presentation theorem given by Goodard and Handelman, which says, well, we can represent all metrically complete unital Abelian groups in this way, as you take a compact Hausdorff space. To each element you associate a label, or also called a denominator. Anyway, you associate either R or 1 over nz. Maybe to a point you associate R, to another you associate 1 over 2z, into another z. And then if you define the set of continuous functions from x to r, which respect these constraints, pointwise constraints, so at every element the function is allowed to take value only on these subsets of R. This gives a metrically complete unital L group, and all metrically complete unital Abelian L group can be represented in this way. Okay, good. Now we have our base, our representation theorem. But I wanted to share that we wanted to turn these into a categorical duality, so that we have representations also of the good maps, and we have a faithful mirror. But maybe you can see some obstruction to having, the representation that Goodard and Handelman gave was not a one-to-one correspondence. For example, if you take a point with denominator, so with attach the label z, the associated L group will be z. But also if you look at the unit interval 0, 1, with every point associated the label z, then the L group associated to it will be the continuous function from x to z, which is isomorphic to z in this case. So we have two non-isomorphic objects that give two isomorphic L group. To get a one-to-one correspondence, we need to add some condition to these representations, which is a sort of separation. So we add this, that given x and y distinct, then by Hausdorffness we know that there might be open neighborhoods that separate the points. Here we ask also that that everything that is left out from these two neighborhoods has labels R. So as an example, this is the main example. Take the unit interval 0, 1. This is our compact Hausdorff space, and associate to each element. Well, if it's a rational, you associate 1 over QZ, the denominator. Otherwise, you associate R, if it's irrational. This satisfies this separation condition, because if I have two different elements, I can find an irrational number between them, and I can use these two open sets. Okay. Second condition. Second reason why this is not a one-to-one correspondence is the following. So, if you take this space with an accumulation point and a sequence converted into it, and I associate to every point 1/2 Z, and I consider another one which is practically the same, except that on the accumulation point I associate 1/4 Z, these will give me the same L group. Although they are different, they give me the same group, essentially because although here in the accumulation point in the second component I allow the value 1/4, I can never reach it with a continuous function that respects all the other constraints. So again, we don't have we need to add a condition to obtain a one-to-one correspondence, and this is a sort of continuity of these labels. Maybe semi-continuity would be a better name. Technically, it means that for every n, the set of x such that the x is contained 1/n is closed. And for example, here this is satisfied because what are we saying? Take n, for example, n equals 4, and here we are asking that the set of elements whose denominator is divides 4, so these 4 things is closed. And then we get our notion of normal A space, which, in fact, if compact Hausdorff space is a generalization of 0, 1 with a compact Hausdorff topology, there's a precise sense. For example, any compact Hausdorff spaces are precisely the closed subsets of arbitrary powers of 0, 1. Here, this normal A space is a generalization similar to this of this example of 0, 1 with denominators. And the condition we have here are, so we have a compact Hausdorff space, this bunch of labels, or that we call denominators, and they should satisfy separation and semi-continuity. Okay, now, with this we get a duality for these metrically complete unital Abelian L groups. So they are really the same thing as these normal A spaces, just they are flipped upside down with the directional functions inverted. Okay. Oh, and this specializes to the two dualities I mentioned before. So in case all the labels are R, then I'm not imposing any restriction on the continuous functions, so I get C of x R. Instead, if I impose that all labels are Z, well then, the separation condition actually guarantees that there are enough closed subsets to separate the points. So I get an arbitrary stone space, and the L group associated to this stone space is continuous function from X to Z, which is not exactly the same thing, but quite similar to the Boolean algebra of closed subsets, which is this one. In particular, if from C of X, Z, I look at all the elements between 0 and 1, I get this Boolean algebra. Okay, so just to conclude, we've seen some categorical, some mirrors, so some surprising dualities between different words. These words seem to have almost nothing in common, and yet they contain the same information. And in fact, Baez and Dolan said that an equation is only interesting or useful to the extent that the two sides are different. For example, the equation e to the I omega equals cosinus of omega plus I sinus of omega is far more interesting and useful than 1 equals 1. Precisely because these have much different shapes, just like Dr. Jekyll and Mr. Hyde. Thank you.